Hello. So this is the next chapter for fluid mechanics. Chapter name is fluid pressure and measurement. So as you can see on the screen, we have the questions. Today we will do all previous year questions of second chapter, that is fluid pressure and measurement in fluid mechanics for civil engineering, whatever we have got in GATE in previous years. So these are the questions. As we can see, we will be solving them. So let's start one by one. So very first we have the 1 mark questions. So in this I am having question number 1. Let's read this. The reading of a differential manometer of a venturimeter placed at 45 degrees to the horizontal is 11 centimeter. So a differential manometer is attached into venturimeter. For now you don't need to understand what is venturimeter. That is in further chapters. So here we have to see the differential manometer is there, which is attached to a venturimeter placed at 45 degrees to the horizontal is 11 centimeter. If the venturimeter is turned to horizontal position, the manometer reading will be. So we need to remember that, see, till now we don't know anything about venturimeter, but we know that differential manometer readings will not be affected with the inclination or angle of venturimeter. So whatever angle is there, there will be same manometer reading. So from the horizontal, if the differential manometer is having 11 centimeter reading, it will be same even if the venturimeter is inclined for 45 degrees. So this is 1C. C is the answer. This question came in GATE 2005 for 1 mark. Now question number 2, as we see, is an inclined manometer shown in the figure below. The reservoir is large. Okay, here we can see there is a reservoir. This is the reservoir, and its surface may be assumed to remain at a fixed elevation. Okay, so the surface is having with a fixed elevation. A is connected to a gas pipeline, and the deflection noted on the inclined glass. See, this point A is connected to a gas pipeline, and the deflection noted on the inclined gas tube is 100 mm. So when there was a gas pipeline connected, became the change in the pressure, and the pressure in the inclined manometer we can see is 100 mm. 100 mm they have shown here. Assuming theta is equal to 30 degree and the manometric fluid as oil with specific gravity 0.86. Manometric fluid is having specific gravity 0.86. The pressure at A, we have to tell what was the pressure at A. Let's assume there is a point. See, pressure at A is nothing but pressure here. Okay, because till here what we have? We have gas in full liquid. Okay, so whatever pressure here is the same as pressure at A. So if we calculate, let's say this is the point, we name it as C. So we know that pressure at C will be equal to pressure at A. So if we calculate the pressure at C, we know the pressure at A because this is the same fluid here. Now if we see the height here, what will be the height, total height of the liquid? We can say the height is 100. Height is, this is 100, this is theta is equal to 30. The height of the liquid raised in the inclined tube will be 100 sine 30. 100 sine 30. 100 sine 30 means sine 30 is 1 by 2. So the height which got raised was 50 mm. So this height we know of the liquid, right? So this height is with respect to the liquid that got raised. Okay, and what was the liquid that was having with the density of 0.86? We have to say we have to show the pressure. Okay, and see 0.86, we can say the height is 50 mm with respect to the 0.86 dense 0.86 specific gravity liquid, any liquid. But here we can see the answer is in waters, in terms of water, not in terms of the given liquid. So we need to change our answer into the terms of water. So how we will change that? So nothing, we have to do, see, 50 mm into what is the specific gravity of the fluid, 0.86 divided by specific gravity of water. So what is the specific gravity of water? Is 1. How? We are taking it as 1.86 with respect to 1. So it will become 50 into 0.86, that comes as 43 mm of water. 43 mm of H2O, that means water. So answer will be B. Okay, it will not be 86 mm, it will not be 100 mm, it is 43 mm of water. That is also gauge pressure, not at all vacuum, because it is attached to atmosphere. So this is done. We have done the question 2 as well. Now let's see, there is question number 3. In a static fluid, the pressure at a point is equal to the weight of the fluid above, equal in all directions only if the viscosity is 0, always directed toward and downwards. So see, we have seen that any liquid, if the fluid is static, right, there is no movement. Static means no movement in the fluid. So if the fluid is static, the pressure on the fluid molecule will be equal in all directions. So with this we have equal in all directions. Why this is happening? Because in static fluid there is no shear stress, right? Fluid is not at all moving. So if there is no movement in fluid, there is no shear stress. So if there is no shear stress, that means tau equal to 0. This implies we have equation by Newton's equation, that is Newton's viscosity law. Tau is equal to mu du over dy. So with this we know that du over dy is also 0. Hence if there is no shear stress existing, it is same regarding of whatever the fluid is real or ideal. So we know the fluid will be having same pressure in all directions, as shear stress is also 0. That means we are done with question number 3 as well. Okay, so let's see 2 marks questions now. 2 marks questions. Question number 1 is a closed tank. There is a closed tank contains 0.5 mm thick layer of mercury. So let's draw first. We are having, let's say, a closed tank, something like this. Okay, now we are having 0.5 mm thick layer of mercury, which is having specific gravity 0.6. okay, at the bottom. So at the bottom we have, let's say here, mercury, that means Hg of 0.5 mm. So it will be of specific gravity Sg, no, there is 13.6, and the height is also given, that is 0.5 meters. Okay, and then this is at the bottom. A 2 meter thick layer of water lies above the mercury layer. Okay, so above the mercury layer we have 2 meter thick water. So let's say there is 2 meter thick water layer H2O, which is having specific gravity 1. Okay, then there is a 3 meter thick layer of oil, which is having specific gravity 0.6. So let's say the oil with orange. So 3 meter, okay, let's make it as well. This is 2 meters, and then oil is there, that is 3 meters. So oil with specific gravity 0.6. The gauge pressure at the bottom of the tank is 196.2 kilonewton. So let's say this is the tank. Okay, if the tank, it may be filled till here, right? Tank's height can be more. So there will be some pressure. Due to that, the total pressure at the bottom is 196.2 kilonewton per meter square. The density of water is 1000 kilogram per meter cube. We have given rho of water 1000 kg per meter cube, and pressure at the bottom is given, right? So, and the acceleration due to gravity, okay, g value we all know 9.81 meter per second square. Value of pressure in the air space is, so at the bottom we have given the pressure value 196.2 kilonewton per meter square, right? So we have to calculate the pressure at the airspace. Let's see, this is the airspace, we are having pressure. This pressure we need to calculate. So how will we calculate this pressure? So see, at the bottom will be the total pressure above this bottom point particular. So we will be adding all the pressures, right? And then it will give the answer. So let's do it. So we are having total pressure is, first of all, P. Okay, P is the air pressure. Then oil is there with 3 meter height and specific gravity 0.6. So we are having 3 meter height. See what equation we'll put, rho, g and h. Density for the first liquid, rho 1 g h1. So we have rho is 0.6, g is 9.81, and h, what is the value of h, is 3 meters, right? So this is the first liquid. Then we have water. So water is rho gh. Rho means 1 is the density, 9.81 is the is the acceleration due to gravity, and its height is 2 meters. And then next is rho gh again. Rho is 13.6. 9.81 into 0.5 is equal to what? So this total value is equal to 196.2 kilonewton per meter square. So let's calculate. We will get directly the value of P here. So P plus, so if we calculate 0.6 into 9.81, and so this we will get, this is 17.658 plus 9.81 into 2, 9.81 into 2. So this is 19.62 plus 13.6 into 9.81 into 0.5, 66.708 is equal to 196.2 plus 19.62 plus 17.658 minus 192.2. It is 92. So we are getting the value of P is 92.214 kilonewton per meter square. So only pressure of air is this much. See, pressure of oil was lesser than pressure of air. Even pressure of water and pressure of mercury is lesser than pressure of air. We are getting the total pressure of air is this much from the equation. Okay, so this is the, okay, let's see what is the answer. 241, 92.241. We are getting the answer A. Okay, so let's do the question number 5 here. Question number 5 is, 3 fluid system immiscible is connected to a vacuum pump. Okay, there is 3 fluid system just like this was there. Only difference is here it was air, that means atmosphere, and but here it is connected to a vacuum pump. And then the specific gravity values of the fluids S1 and S2 is given. Okay, and P1 is what? Vacuum. There is pressure, but we don't know that. And there are two fluids, fluid 1 and fluid 2, with specific gravity is given and with the specific height of their lengths is also given. Okay, and this is finally connected to water, that is fluid 3, with atmospheric pressure. And we are having unit weight of water, this atmospheric pressure 95.43 kPa. The gauge pressure value in kilonewton per meter square up to 2 decimal places of P1. We have to calculate the value of P1 here. So can we work this with the same concept we have studied in previous question, that is question number 4. In previous question we were given with the pressure at bottom and we have to calculate the pressure at the upper side, at the top. So we know pressure at bottom is summation of all the pressures above that. If these conditions we apply, same condition if we apply in this question number 5, we can calculate P1. Here also we had to calculate P, here also we had to calculate P1. But if only if I know the pressure at the bottom of this tank, that I know, that I can calculate here. How? See, we have two ways to give the pressure, right? There is one more fluid, P atmosphere. So this, at this particular point I can calculate the pressure by this equation. That means I have given the height. Okay, for this particular point the pressure will be of the liquid above this point. So if I say pressure below fluid 3, pressure below fluid 2, at the bottom of fluid 2 I can say. So pressure at bottom of fluid 2, so that I get of fluid 2 I can say, that will be equal to rho gh. And we have, okay, P atmospheric, first of all, P atmospheric plus height of the fluid, right? That is rho, that is density. The density I have given. Okay, is there anything mentioned? Unit weight gamma w directly. So gamma w I have given directly. I can use rho h gamma w, right? The gamma w is nothing but rho into g. So I can say P atmospheric is 95.43 plus kPa is nothing but kilonewton per meter cube. So height is 0.5 and we have 9.81. Here I will get question 95.43 plus 0.5 into 9.81. I get 100. I get it 100.335 kilo Newton per meter square or kPa. Okay, so this is the pressure value where at this particular point. Now if I get this, I can directly say that this total pressure is equal to nothing but P1 plus S1 fluid, right? So rho 1 G or rho G and H of S1 fluid plus rho G H of S2 fluid. So I can directly say that P1 is, I don't know, I have to calculate, plus rho, and directly they have given specific gravity. So this is 0.88 of what? Water. Water is rho. So I can directly put rho and G is nothing but gamma W. 0.88 gamma W into height. What is the height? So height is 1 and this is 1.5, 0.5. So it is 0.88 into rho into 0.5 plus rho G of this particular specific gravity is 0.95 of gamma W, and height is, this particular fluid is having height 1. So it is 1 and total pressure is 100.335 kPa or kilonewton per meter square. So if I calculate gamma W, I can put the value of gamma W, that is 9.81. So for this I get final value as P1 86.69 kPa. This is the pressure value, 86.69 kPa. This particular question came in GATE 2018 for shift 2, and we have the answer is 86.69. Okay, but this 86.69 is nothing but with respect to the atmosphere. Okay, I have to calculate the gauge pressure. So gauge pressure I can give, that is nothing but this P1 minus atmosphere. So I will minus it. So I have 86.69, and what is the atmospheric pressure? It is minus 95.43 kPa. Then I get the answer as 8.73, that is negative kPa or kilonewton per meter. This is the pressure. So with this I got the answer as minus 8.73. P1 value is minus 8.73 kilonewton per meter square. Kilonewton per meter square. So this is the answer here. So now we have next question, that is question number 6, in which they are saying the figure shows a U-tube having a 5 mm is to 5 mm square cross section. So we are having a U-tube manometer which is having square cross section, not circular. Now that is filled with mercury which is having specific gravity 13.6 up to a height of 20 centimeter in each limb. So in each limb it is 20 and 20 centimeter, and both limbs are open to atmosphere. Now if 5 centimeter cube of water is added to the limb, 5 centimeter cube of water is added to the right limb. In the right limb, if they add 5 centimeter cube of water, the new height in centimeter up to 2 decimal places of mercury in left limb will be, if we see, we are having something like this. Okay, so this is a U-tube manometer in which they have filled the mercury up to 20 centimeter, means there is mercury till 20 centimeter, and mercury is having specific gravity of 13.6, so Sg of 13.6. now the cross section of each limb is 5 centimeter is to 5 centimeter. Then and the total limb height is 50 centimeter. Now we can say, see, if they put water in this, then there will be some change. They are putting water from right limb, so there will be some changes into the mercury level that will go down. Let's say that will go down, that means how much it will go down we don't know. Let's say that goes down till x. Okay, so the new height, now we have filled water, so that goes down, this mercury level goes down till x. Now the new height we have, that is 20 centimeter minus x. Okay, and okay, let's change it first to meters, because it will be better for our calculations. Is 0.20 minus x, and if mercury level is coming down to x mm here, it will go up till x here. Here it will be mercury level till x. So this is what, x. So the total limb length, now new limb length, will be 0.2 plus x. Now we will put the equation. So this limb is attached with water, this is attached with water, and this limb is free to atmosphere right now. Okay, so from right to left we can calculate the pressure and we can find out the height. Okay, this is not circular, right? So if I want to calculate the height, how much water I am putting, see, I am putting the water of volume 5 centimeter cube. If I want to convert it into height, I will get, what will be the height of the water? That will be 5, see, I have area, I have centimeter cube, I will get the height as water. So this is mm and mm. Okay, so I know the height will be volume upon area, right? Volume is 5 centimeter cube, and we have this area in meter in mm, right? So I will put 5 into 5 mm, and I will change the centimeter cube into mm cube. So it will become 1000. I will multiply it by 1000, and I'll get the final answer as 20 centimeter. So the water height that came into this is 20 centimeter, that means 0.2 meters. Now since I know in both limbs, let's say this is P1 and let's say this is P2. Okay, pressure will be same. Let's say this is P1 and this is P2. Pressure will be same in both limbs. Ultimate pressure at the bottom, it will be same, right? So let's say this is the at the bottom, even if it is from here or here, it will be same, right? So I can say that P2 is equal to P1. That means I can say what is P2? P2 is 0.2 plus x height of mercury, right? So rho is 13.6 into 1000, and okay, this is rho gh. That means, and that will be equal to 0.2 into rho. I have multiplied only rho, and I will multiply by g as well, 9.81. So 0.2 into rho, that is 1000, into 9.81. okay, there is 0.2 minus x, so plus 0.2 minus x of mercury again. So 13.6 into 1000 into 9.81. So if I calculate it, I get the final answer of x that I have calculated. It comes as 0.735 centimeters. So the x is 0.735 centimeter. What is the question now? The new height in centimeter up to 2 decimal places of mercury in left limb. So the new height in left limb I have to say. So in the left limb the height is 0.2. That means now 0.2, because answer I have calculated in centimeter, it will be 20 plus x. So 20.735 centimeter. This is the answer of, okay, we don't have answer, I will put 20.735. So by this I have calculated question number 6 as well. Question number 7 is 2 pipelines, one carrying oil, mass density 900 kg per meter cube. Okay, so I have 2 pipelines, one carrying oil, mass density of 900 kg per meter cube, and other water, and these both are connected to a manometer as shown in the figure. By what amount the pressure in the water pipe should be increased? Okay, so that the mercury level in both the limbs of the manometer becomes equal. Okay, I have to equalize the mercury level. That means if it is 20 here, this is 20 here, this is base, right? So I have to increase the pressure level so that this becomes 10 and this also becomes 10. This much height I need to get, right? So let's name them first. So I have, let's say this is limb, this is water is limb A and oil is limb B. Okay, so what is the pressure at both the limbs here? I don't know. On both the pipes, this is pipe A, this is pipe B. We don't know the pressures in both the pipes, but we know all the conditions here. Everything is given. I can calculate at least the pressure difference. So the pressure difference, how I can calculate? I will make the equation. Okay, so let's say the datum first I need to select. I will select the datum as this one. Here both limbs are covering properly. So if I write the equation for this datum, from right to left I will go downwards, and downwards positive pressure, you need to remember pressure will be downwards positive and upwards negative. I will put one equation, only one equation, and that will do everything. So let's say, see here pressure will be PA, that I don't know, PA, okay, plus what is the water height, 1.5 into its density 1000 into 9.81 rho gh, okay. Until here the then next fluid is mercury, plus pressure of mercury, what it will be, that is 0.2, right, 0.2 into density of mercury they have given here 3550. If it is given there I will use this 550 into 9.81. so this is the pressure here in the right limb. Now I am going to the left limb, from right to left, upward. Upward means negative. So I will put in this equation negative of, again there is oil, fully oil, this above the datum line. So oil is having 3 meter height into, oil is having, see oil's mass density already given. So 900 into 9.81, and there will be pressure of P. This is equal to 0. This is how we write the equation for pressure. Now in any manometer, so if I calculate this PA minus PP, this comes as minus 1.5 meter of water. So everything we have changed in terms of water because we have multiplied everywhere with the density of water. So this is minus 1.5 meter of water it came. Again in second case, this, let's say this is the case 1, and in second case what was happening, they have equalized the mercury level in both sides. Then we know that the mercury will come here and here, right, 10 and 10 centimeters. Now what I can do is, see datum we select the line below which there is only one liquid, right. Here also now we have mercury, okay. So in this case, to avoid extra calculation, I can change my datum. Otherwise you can take the same datum, but here I can see that below this everywhere is mercury, right. So if I do the equation in second case, this is case 2. So if I write the equation, now I need to, the question was by what amount the pressure in water pipe should be increased. In this water pipe, that means water pipe A, how much pressure should be increased so that I get this level, okay. So if for this level, what will be the pressure difference, that we will calculate now. Let's write the equation again. So I have now, we must have increased some pressure. So it is not PA anymore, it is something increment. That's why this height came down. So now I will take PA plus delta P. So PA plus delta P is nothing but, okay, and before this, see this new height is water height. Now this whole height is water height. Previously this was 1.5 meter and now 0.1 meter as well. So total height became 1.6 meters. So I will use 1.6 meters here, plus 1.6 into 1000 into 9.81. Now minus from 3 we will minus the 10 centimeter height. It comes as 2.9 into oil density was 9000 and 9.81 multiplied by this, and in second limb we haven't changed the pressure, it is PV equal to 0. With that I will calculate the delta P. This comes as PA minus PB, right. We get, okay, this PA will go other side and PB will go that side. It becomes PB minus PA. PB minus PA, and the whole change is plus 1.01. Okay, we have PB minus PA as 1.51 plus 1.01. This comes as 2.52 meters of water. This is itne meters of water. I have to give it in pressure. Okay, so height is given. I will multiply it with G. I will get the answer 2.52 into 9.81. It comes as 24.72 kPa. So the answer is 7th A. So this is the 7th question. Now we have question number 8. We can see here a U-tube with both limbs open to atmosphere contains two immiscible liquids of densities rho 1 and rho 2. So there is a U-tube which is having two liquids rho 1 and rho 2 under equilibrium distance h is given. So I have to calculate the height, this h. That means, see, first of all select the datum, and both are with the atmosphere, right? So if I select the datum, below that everything should be same liquid, right? So I can select this as datum, that is datum. So I can calculate the height as, let's write the equation first. This is, let's say this is A and this is limb B. Okay, there may be some pressure here PA, there may be some pressure here PB. If I write the equation, and from anywhere, if I am going down, I will see, if I go from right to left like this, if I am going down positive, going up negative. If I am going left to right, if I am going left to right, down positive, negative, anything I can do. So PA plus rho 1 into G into height is L minus H. This much height is L minus H. So it is L minus H. Okay, minus rho 1 into G into L minus PB equal to 0. See, and both the limbs are open to atmosphere, right? Both the limbs are open to atmosphere. See, it is given here. If open to atmosphere, atmospheric pressure will be same. So PA and PB is nothing but P atmosphere. So by this, can I cancel this PA and PB? Plus minus P atmospheric will go, and I will be left with this much. So rho 1 G L minus rho 1 G H minus rho 1 G L. This is rho 1 G L equal to 0. From every, okay, I can take it common and I can cancel it out. So I get left with H. In this diagram they have mentioned it as rho 1, but it is not rho 1. Contains two immiscible liquids, rho 1 here and rho 2. This is rho 2. This is rho 2. Okay, so if I change the equation now, I am having, see, this is rho 2 GH, rho 2 GL minus H minus rho 1. Okay, now it is correct. So I get here as rho 2 G L minus H. So rho 2 GL minus rho 2 GH, rho 2 GH. I need to get rho, see, G and G will be get cancelled. So rho 2 H is equal to rho 2 L minus rho 1 L. L I will take common. H is nothing but rho 2 minus rho 1 upon rho 2 into L. So that becomes 1 minus rho 1 upon rho 2 into L. So 1 minus rho 1 upon rho 2 into L is answer A. So question 8 is having answer A, right? So I hope you got an idea of how to calculate the manometric questions and what is the simple logic behind them. So by this previous year questions study, we have had an idea that what type of questions will be there and what type of questions we need to use. So thank you everyone.